Well, how's it been, Fred?
Oh, I've been good. That last chapter was kind of a doozy.
Well, are you ready to move on to the next one?
I hope so.
Good. Um, this chapter is about a chemical equation or molecular reactions that occur in aqueous solutions. Aqueous solutions. Now, whenever chemistry occurs, that means the two reactants had to come together and actually collide. There had to be a collision of some sort for chemistry to occur. Or if it's just a decomposition, one thing can decompose into two things. But generally, if we have two reactants, they need to be in proximity to each other. And if you think about this in terms of maybe a pile of one material, so let's say I have a chemical reaction that I'm excited about, and this is it, right? I'm going to make A and B come together to form C. Well, if I have a pile of A and it's solid, right? And I have another pile of my chemical B here, all right? And it's solid also. If we mix two solids together, the likelihood of getting an effective or efficient reaction is very slim because these two solids, when we see them, we might think, oh yes, they're really well dissolved or divided in terms of ground up and stuff. But that's usually not actually what's occurring at a molecular or atomic level. The material, much of the material is inside the kind of clumps of solid that you're seeing. And so in general, chemistry will occur more favorably if I can take my A and dissolve it. And when we talk about aqueous, do you remember what aqueous means?
AQ means dissolved in water.
That's right. AQ means dissolved in water. That means aqueous. Aqueous means dissolved in water. Very good. And in chemistry, you often dissolve components in other solvents, not just water. But we'll talk about, and we won't talk about those kind of chemical reactions in this class, okay? So the idea here is when you dissolve something in water, then all the individual entities, whether they be molecular or ionic, can separate and chemistry can really occur because each entity is interacting with another, okay? So at a molecular level, right? So we're going to look at this type of a chemical reaction and we're going to kind of use it to answer lots of questions about chemistry in general. Before we get too far though, we have to kind of define some terminology, okay? A solution is a mixture. It's homogeneous, but it's a mixture of two different kinds of compounds. And generally in a solution, you have what's called a solvent. That's the component that's in the largest concentration. And then you have a solute. Now, our classic example of a solution, right, is where I have a container of water and I put in it some salts, specifically in this case, the salt is sodium chloride, all right? The sodium chloride dissolves and I get a solution. Here my solvent is the water, right? This is my solvent. And sodium chloride is what we call our solute, okay? And solute is the substance that's usually in a lower concentration. The term concentration means basically the amount of solute to solvent, right? And we have a variety of ways to express concentration. And we'll introduce some of them here, but mostly you'll learn about the different ways of expressing concentration in lab, okay? Now, dilute solution, hopefully the word dilute is familiar to you. It's essentially indicating that we only have a little bit dissolved, a little bit of solute. Now we can dissolve more and more and more solute until it gets to a point where we say the solution is concentrated. Now, if a solution is concentrated, what's occurring is that the solution can no longer dissolve any more solute. All right, the solvent can't dissolve the solute, so you can't put any more of your solute into solution. Notice how, I don't know if you've ever added salt to water and watched it dissolve, but eventually if you add more and more salt, what happens?
A pile of salt on the bottom?
That's right, that's right. The salt stops dissolving. All the water molecules that are dissolving the salt are occupied, and so the salt can no longer dissolve. Now, not just salt can dissolve, though, right? I mean, salt is not the only chemical that can dissolve. Sugar can dissolve too. Sugar, our chemical formula for sugar, I mean, our general chemical formula for carbohydrates or any sugars, again, kind of like salts, there's a general formula. C6H12O6, all right? Now, tell me, does that stand out as a different kind of compound as sodium chloride?
What do you mean different kind?
Well, remember when we were classifying compounds, and we said that all of our compounds could be divided into groups?
Oh, like ionic?
That's right. Which one of these is an ionic compound?
Sodium chloride's ionic because it has a metal. Do you have your periodic table?
Yeah, let me bring up my periodic table. Okay, so
Yeah, right there. Sodium is number 11. It's a metal, so sodium chloride is ionic.
very good. Sodium chloride is ionic. C6H12O6, is that ionic?
No, that is molecular.
Very good. Molecular. So molecular compounds can also dissolve in water. Ionic compounds do too sometimes, often. But there's a difference in how they dissolve. In either case, both can reach what we call concentrations of concentrated solutions where you can't dissolve anymore. And maybe in the olden days, we used to put sugar into cereal.
Olden days, I still do that.
You put sugar into cereal? Yeah. I used to have to put sugar into cornflakes or Cheerios because they just weren't very sweet. I guess I don't eat them very much, but yeah, that's what I used to put sugar. Well, what do you add sugar to nowadays?
Mostly my Fruity Pebbles or my Lucky Charms.
Wow, that's pretty committed.
Yeah, it's good stuff.
Yeah, okay. Now, what happens at the end of your cereal when you're done eating if you've added sugar to it?
Well, that's the best part. There's this big pile of sugar on the bottom with a little bit of Lucky Charm flavor, and it's just so good.
All right. So that bottom pile of sugar on the bowl is like the solution is concentrated. It can't dissolve anymore, right?
Yeah, that's right.
Okay, very good. So you do have some experience with dissolving salts possibly, and most likely for sure, molecular compounds in water, right? Good. Okay, so let's move on here to some new terms. Saturated is another way of saying concentrated. If you're saturated, that means you can't dissolve anymore. And then we have this other term, supersaturated, means that you've dissolved more than you can.
Well, I thought you said it stops dissolving.
That's a good point. So how can it be supersaturated? Well, what happens is the amount that you can actually dissolve, which we call the solubility, the amount that you can actually dissolve can vary based on the temperature, all right?
Yeah, I know that.
Oh, really? You do know that? How do you know that?
Oh, because I am a cook. I cook breakfast sometimes, and I make my own syrup when we don't have any.
You make your own syrup. That's pretty impressive. What's the recipe for syrup?
Well, you put in lots of sugar and a little bit of water, but if you keep heating the water, then all the sugar will dissolve.
Very good. So you recognize that at higher temperatures, more solute can dissolve into the solvent, right?
That's right.
Okay, very good. So unsaturated, right? That's another word that we're probably now can understand, right? Means that it's not what?
Not concentrated. You can dissolve more.
Very good. Excellent. Now, the solubility rules are available to us to let us know what kind of ionic compounds are soluble. Because as I said, not all ionic compounds are soluble.
Where'd you get this table?
Well, it's in our book, but also it's on the back of our...
Oh yeah, that's where it looks familiar. I knew it looked familiar.
Yes, it's on the back of our periodic table. that you guys printed out for yourselves, right? So these are our solubility rules. Now let's use some of these solubility rules to determine whether a compound is solid or soluble. Soluble. Now that soluble means, again, it dissolves in water. And again, these are the solubility rules for ionic compounds, so no molecular compounds on here. But the rules basically allow you to look at the ion or the ionic compound and find the ions that are in it and then find a rule that relates to it. These first four rules are about compounds that are generally soluble. Last two are about compounds that are generally insoluble. But recognize also that a lot of them say except at the end, so you have to read the exception clearly. Okay, so let's look at this example. Which of the following compounds are expected to be soluble in water? Calcium carbonate. What do you think? Is calcium carbonate soluble?
Can I look at the solubility rules?
Yes. I don't mind if you look at the solubility rules, and I want you to. Every time you have to answer a solubility question, I want you to look at the solubility rules. So most classes, they ask you to memorize the solubility rules. I'm less interested in you memorizing them and just using them frequently. I feel that if you use them frequently, it'll stick in your memory more effectively in the long term, which is really important to me. So tell me, what do you see? Any rules about this compound, CaCO3? Did I tell you what the name of that compound is?
Oh, I think you said it, but I can't remember.
Well, why don't you try to figure it out?
Ca is calcium,
That's right.
and then you can just slide over a little bit.
Oh yeah, there we go.
I can't see the ions.
Okay, what do you see?
There it is, calcium carbonate.
Very good, calcium carbonate. Now let's use our solubility rules to determine whether it's soluble. Okay? Anything in there?
I don't see anything about calcium. I do see in Rule 6 down there, it talks about carbonate.
Very good. What does it say?
All salts that contain carbonate are insoluble. There we go.
Uh-oh, but there's some exceptions.
Oh, except those of Group 1A. What's that, Group 1A?
Remember, that's the periodic table. That's our alkali metals, these ones.
Oh, yeah, okay. Except Group 1A, what's the rest of it say? And ammonium ion. Okay, so that means that calcium carbonate is not going to be soluble.
Very good. Not going to be soluble. How about this next one?
Oh, that I know that name. That's iron chloride.
Iron chloride, is that it? Are you sure?
Oh, I guess there's more. Do we have to put in a number?
We do have to put in the number. Very good. How do you know that?
I can't remember.
Well, because remember, iron is a transition metal, and it has multiple oxidation states or charge states, right? Therefore, we have to let people know what iron we're talking about when we say iron chloride. And we indicate that number. What does that number tell us?
It tells you the charge on the iron ion.
Very good. That was very good. Iron ion is a hard thing to say, huh?
I've been practicing.
Yeah, that's good. So, what would this be? Iron what chloride?
Iron 3.
That's right. Iron has to have a +3 charge because the chloride ion always has a -1. Now, any rules in here that talk about those ions?
Oh, Rule 3. Rule 3 says that chlorides, bromides, and iodides are soluble except with Ag, silver, lead, and what's Hg?
Mercury.
Mercury. So, yeah, this one is soluble. Iron chloride soluble.
Very good. How about lead chloride?
Yeah, it should be. Read that one again. Chlorides, bromides are soluble.
Okay. What about the exceptions?
Oh, yeah, except silver, Pb. Oh, yeah, okay, so no, this one is not soluble.
Very good. Not soluble. Excellent job. All right. Good work. We're getting into understanding the terminology for solutions and understanding what it means to be soluble and how we can determine the solubility of ionic compounds using our solubility rules. Good job.
Thanks.